Hello and welcome to video 50. For those of you who are my students, and I'm not going to be there tomorrow, and you've ever noted that in class I sound kind of like my videos, well, today that's certainly true because I'm not actually there. My daughter's sick. But let's talk about electric potential. So what we're going to look at is we're going to look at a situation where you've got four charges on the edges of a square. And what I want to know is, what is the electric potential at the center there? Before we can talk about that, though, I just want to take a second and remind you of a couple things. What is electric potential? What does it mean? What are the sign conventions? How do we calculate the electric potential from a single point charge? And then how do we calculate the electric potential from many point charges? So electric potential, if you recall, is a way of talking about the energy that a positive charge would have there, specifically a 1 coulomb positive charge would have if you were to place it at a particular location. In other words, V equals work over charge. It's an amount of energy per charge. So whereas electric fields were a way of talking about the force per charge, electric potential allows us to talk about energy per charge. And we're going to start off by looking at a single point charge. So if you've got a positive charge here, those of you who are in class may remember we drew the electric field lines. They would go away from a positive towards a negative. And the electric potential lines are always going to be perpendicular to that, because when you move perpendicular, you're not going to do any work. You're also going to notice that near the charge, they're close together, and the further away you get away from the charge, the further these things get separated, these lines of equal potential or equipotential. And you can think about this almost like a mountain. So if I was to actually sketch a graph of what the electric potential of this looked like, let me pick a thicker marker. If this is the electric potential or the voltage, and this is the distance from the charge itself, you would find near the charge you've got a very positive electric potential. Further away it gets less. And where it gets to zero is at a distance that is infinitely far away. So the way you calculate voltage or electric potential from a positive point charge is it's K Q over R. Really similar to electric field, except it's not squared. It's just over R. And for positive test charge, or for positive charges, you're always going to get a positive electric potential. If I was to repeat this for a negative charge, it would look really similar, but it wouldn't be exactly the same. What's going to be different, as you can imagine, is now the electric field lines are going to go in. You can still see that the electric field is strongest near the charge, they're closest. And if I go to draw lines of equipotential, equal potential energy per charge, it's still going to be much closer near the charge and gradually getting further and further apart as you get away from the charge, because the force here is much weaker, so you have to go a greater distance to change it the same amount of energy. We talked about that in class. The difference is, if I was a positive charge, and whenever you're talking about electric potential, you always talk about it as if it was a positive charge. Positive charges actually want to go towards negative. So the lower the electric potential, closer to the negative charge, and it's actually going to be greater, or at least more positive, the further away you get. And you still want it to be zero when a charge or test charge is infinitely far away, but you want it to be negative when it's close. So if we look at the electric potential versus the distance, it's actually going to be very negative close to the charge and go to zero. So these are sort of mirror images of one another. Really positive potential near a positive charge, really negative potential near a negative charge, and in either case, when you get infinitely far away, you're going to have zero electric potential. So how does this allow us to calculate the electric potential from a group of charges like described here? Well, let's take a moment and draw that and And let's give these charges names. I'm not very creative, so I'm going to call them A, B, C, and D. And if you read the problem, it goes from the top clockwise. This is plus 3 coulombs. This is, actually let me use a different color. This is going to be plus 3 coulombs. This is going to be minus 2 coulombs. This is going to be minus 4 coulombs. And this is going to be plus 6 coulombs. The distances, as you can see from the picture, are going to be 2. And just to make this really simple, we'll call these 2 meters. So this is 2 meters, 2 meters, 2 meters, 2 meters. Those of you may recognize this is a special triangle. If this is 2, instead of being 1, 1, radical 2, it's going to be 2, 2, 2 square root of 2. And those will become important because what we're actually going to do is we are going to calculate the distance. Well, we're going to need that distance there, so to the midpoint, instead of being 2 radical 2, it's going to be half that, or it's going to be square root of 2. So every single one of these 4 charges is going to be a distance of square root of 2 from the center. So if I want to know, and this is the beauty of working with electric potential, it's so much easier than calculating electric field because we don't need to deal with components. There's no direction. It's not a vector, it's just a scalar. So if I want to know the total electric field at the center, it's going to be the electric field from A plus the electric field, I shouldn't say electric field, I'm misspeaking. The electric potential total is going to be electric potential from A plus the electric potential from B plus the electric potential from C plus the electric potential from D. You literally just add them. So if we're going to do that, that's going to be K times charge A over the distance from A plus K times charge B over the distance to B plus K times charge C over the distance to C plus K times charge D over the distance to D. Now, some of you may have noticed it's the center of a square. Aren't they all the same distance? And they certainly are. That distance we've discussed is square root of 2. So I can rewrite this by pulling out the K, because all of these have a K, and that distance for all of them is square root of 2 meters times QA plus QB plus QC plus QD. Or, when you plug in the numbers for the charges, that's going to be plus 3 coulombs, minus 2 coulombs, minus 4 coulombs, plus 6 coulombs, times K over square root of 2, which is going to give you a net charge here that is going to be plus 3. So when I plug in K, 9 times 10 to the 8th, or 10 to the 9th rather, newtons, meters squared per coulomb squared, times 1 over square root of 2 times 3 coulombs. And you plug all that in, you're going to get an electric potential that is 1.91 times 10 to the 10th volts, or volts are also known as joules per coulomb. Now, while I may have been talking a while here, if we had been calculating the electric field at the center, I would have been talking a lot longer. This really does simplify our life. So again, just reviewing, electric potential is a way of talking about the amount of potential energy a charge would have without having to know the charge ahead of time. Or, more specifically, the potential energy a 1 coulomb charge would have if you placed it, in this case, at the center of the square. Sign conventions are that electric potential is very positive near positive charges, it's very negative near negative charges, and it's 0 at infinity. If you have a cluster of charges like this, or a distribution, and you want to know the total electric potential at any one point, you simply calculate the electric potential for each charge and then add them. No need to worry about components because this is not a vector. It's just a scalar. So it simplifies significantly. I hope that this helps you. Certainly my students, it'll help you with your assignment. And I hope to be back very soon.